Oh, right. So how many of you watched that movie before? Not really. Okay, not a lot. Okay, it was actually one of the most entertaining movie I watched this first half of the year. You know, sometimes people have stereotype on a lot of things, and like we typically have a stereotype on Bowser, right? Like we thought he is evil. Bowser must have no knowledge. He is brutal, right? But you know, one thing that I feel very good about this movie is like you feel like every character is pretty cute. Like even Bowser, he has his own, you know, he has his own desire. He has his tiny part, secret spot that he doesn't want any other people know. Like he was so talented. He is so talented in piano, right? Composing, right? Probably not singing, but um, yeah, and but you know, he has a romantic mind. So, you know, sometimes you cannot be restricted by a lot of stereotype. And today we are going to talk a little bit about this for two things. One is that there are a lot of stereotype that you might have regarding computer programming or computer architecture. In addition, another topic that we're going to talk about is also semi-related to Super Mario movie, or Super Mario in general. But before we start, you know, today we are going to do something differently. I know you guys have the Vonima architecture in mind, so let's skip that one. Let's start with this question. So what kind of tricky C or C++ programming language questions have you ever heard before? Go. What kind of tricky like programming question that you heard about C or C++ before? Done. Okay, what kind of tricky C++ or C programming language questions that you ever heard before? like some kind of company love this. What? Pointer? Okay, that's a difficult one. What's the other? What others you have heard? There used to be a question, oh well, I don't know if it's true for now, but 10 years ago, Qualcomm really liked one type of question. But I don't want to tell you right now. But can you guys guess? What kind of question do you think those companies would think someone who aced in C programming language should know? Overflow, overflow, maybe, right?
Good like memory management with the stack and heap and everything.
Okay, so that's one type of question people would ask. What else? Like tricky C or C++ programming language. Pointer, okay, that's one, right? What else? Pointer, yeah, okay, what else? Smart pointer, what else? Okay, so if you go to a website, some website, they will give you a set of tricky C++ programming questions like, what's the fastest way of multiply any number by 9? How to measure the size of any variable without using size of, or without, what's the difference between the first and the second, third and, oh yeah, yeah, okay, write code snippets to swap two variables in 5 different ways, how to swap the first and second byte of an integer in one line statement. What's an efficient way to divide a number by 4? Suggest an efficient method to count a number, test whether something is power of 2 or not, how to check the Indianness of a computer, write a C program, which does the addition of 2 integers without using a plus operator. Write a C program, find the smallest 3 integers, blah, blah, blah. How many of you ever seen this kind of problem before? Okay, right. Which did you see? You mean this one? Power of 2. Okay. Okay. What else? Okay, good to hear that only this one is being used right now. Okay, so one of the one that I have objection about this is actually this. And so, like, okay, so here's the thing. Well, you might not believe that the first question started really fast, right? So these are actually 2 ways of swapping 2 variables. Can you judge which one is faster? Okay, I've seen people voting quickly, so maybe we can wrap up in 15 seconds, right? But this one, people will probably just guess. 5, 4, 3, 2, 1. Time is up. Okay, so based on your stereotype, most of you think it's B. Some of you think it's A. Some of you think it's C. So looking at this one, right? So A and B. So why don't you discuss with your friends? And sometimes you make a guess because you have an intuition, right? Why this guess would work out better. So like, okay, so for example, in multiple choice questions, you might guess C, although if you guess C for in-person midterm, you will miss a lot this time because there's not really, I think there's only one in C because I really hate C for many reasons. I don't like to get a C when I'm taking classes. Like I like to get A, right? So, we have a lot of A's in the answers, but okay. But sometimes you make a guess because historically, okay, I think C is the most, right? So can you discuss with your friend for 90 seconds and talk about why you make such a guess and why do you think that guess is fulfilling the intuition.
Maybe that's doing any kind of logical operation, that's not just compose the store. So it'd be about the same. Yeah, pretty much.
All right, wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, what do you guys get? After discussion, okay, things are changing, right? Okay, what do you guys think? Any thoughts?
Like pretty fast when you have like register available.
Uh-huh.
So like you just copy things around more.
Okay.
If you don't have luxury of having one extra register and you have to like do things to a memory, then
So you say A is faster because?
if you have enough resource to do the computation, like enough space to just copy.
What do you mean by space here? Like a register?
Register.
Okay. But okay. So if you have enough register, then it will be the better one. Okay. But how about B? Because it doesn't really need that many register.
Yeah. So I think like with a limited register with 2 numbers, B is the faster one. So like you don't have to store anything anymore.
Okay. What else? What else do you have in mind? Okay, Brendan.
What I like was so for A, you don't have to ever use the ALU. B, you have to do logical operations, so there's like extra bypassing, so that's why.
So you say for A,
like you don't have to use logical operations. You just load and store.
So, but isn't memory slower?
Oh, then logical operations.
What else? Okay, Jack.
For B, you need to wait for the first to finish. Finish, then you can do the next one. But for A, you can do parallel.
Okay. So that's a good observation. For A, basically like okay, so load A equal to temp equal to A, and once you have that loaded, the other two, right? Assign B to A and assign temp to B. That could be done separately, right? Or say like in parallel. However, for AB, BA, AB, right? Because they are occupying the same resource, so they are pretty much back to back, and there's nothing that you can be done in parallel. Okay, so those are good discussions, right? But sometimes, I mean, seeing is believing, so that's why we need a demo. Okay, so it wants me to log in. Come on. You know, once a while, you need to log in. Okay, so, right, if you remember, previously we have been using gprof to show that in quicksort, the most time-consuming function was actually swapping, right? So if we can improve the performance of swapping, we can actually improve the performance of quicksort. So based on that, right? So I have two different versions of a swap, and I'm going to plug them. Oops. I'm going to plug them into the function of quicksort. So here, come on. Okay, I have two versions of the swap. The left-hand side is the register-based swap, which is the version A. The right-hand side is the exclusive OR version of the swap. So surprisingly, 10 years ago, companies like a big company in San Diego, okay, we don't want to say which company is that. One of the joint company in San Diego was headquartered in San Diego, close to where I live for 6 minutes. 6 minutes away from I currently living now. So for that company, they really love to test this kind of question. They would say, hey, can you try to use only 2 registers or use bitwise operators to write swap function, right? So a lot of examiners, they really like to hear the answer like the right-hand side. So a lot of people will memorize the right-hand side answer and they think this is cool and they think this is faster, right? But let's try to see if that's really the case. So, this is the swapping function we have. And what I do, okay, so this is a very interesting technique. I don't know how many of you tried that before. This is called function pointer. So a lot of you saying about like tricky C programming techniques. And function pointer is one of them. So function pointer is that I declare the function prototype as a pointer. And when I call this function, if I use the function pointer 1, then I can dynamically decide which function that I'm calling during the runtime. So that's sometimes how you can do like dynamic swapping, the dynamic function loading, this kind of stuff. So if you look at the code, what happened here is that, okay, I parse the argument. If an argument 2 is equal to 1, then I will set my swap, the function pointer swap, to the function to the beginning of the function exclusive OR swap. Okay, so the idea of function pointer is basically it's still a pointer. However, remember, right? Code has its own memory address, right? So a lot of like previously, everyone would forget that, okay, code is also in memory. So here is a good evidence that code is part of the memory. So here I'm assigning exclusive OR swap to swap, which means that I'm assigning the beginning address of the code of exclusive OR swap to swap. This is a pointer. And however, if it's set to everything other than 1, it will be the regular or say register-based swap. And then I will generate a random number. And finally, I will run a quicksort. And again, as quicksort is heavily rely on swapping, you can see how efficient, how effective the swapping function would affect the performance. So here I'm running 2 different versions, and I highly optimize these functions. So for version A, they are typically, okay, one more time. Sometimes demo really doesn't help you that much. Okay, so for version A, okay, they are not that different, although except for the very first one, interesting. It's different from the time when I run at home. Okay, so this time it really does the job. Okay, so the longer you know, right? So sometimes you cannot let your computer idle too long because they have really aggressive frequency scaling right now. So the first run, as you can see, is always slower because it was always slower because if I didn't touch the button for a long time, they will dynamically run down the clock rate to 2 gigahertz for this processor. So it becomes really slow and it takes time to ramp up. So now this time I'm fortunate enough, so I run it a lot faster. I click the button fast enough. So as you can see, with version A, all the sort, they are faster than any of the instances for version B, right? So with that, which tells you is that, well, although the exclusive OR swap looks fancier in terms of some of the advanced programmers' perspective, however, if you look at the performance, it's really not advantageous, right? In fact, version A is slightly faster. So sometimes, right, I do feel like people have stereotype on what computer looks like. And in fact, if you ask the same questions 30 years ago for this question, I would probably bet the right-hand side is correct. However, the thing is that, sometimes people just leverage what they got from the previous guys, right? So if your teacher says that, oh, the right-hand side is faster, you just believe it, you never try it again. But unfortunately, I'm not that kind of person. So I tried again and I figured out that the right-hand side is now slower. So I would probably say, right, if a company, they keep having this kind of question, you probably don't want to go to that company. So don't be too sad if you didn't get an offer from that company, because some of their engineers are pretty outdated. And that sometimes explains why a company started going down, right? I didn't say that company goes down. So don't elaborate that too much, right? But their stock price goes down a lot these days. Anyway, okay. For surprisingly, right, a lot of people would think the right-hand side is faster. However, that's not true. The left-hand side is slightly faster. So in a lot of cases like this, right, you learn a lot of tricky C programming or even Python programming. However, are they really contribute to performance? Sometimes not really, right? Like a lot of stuff you guys said, like pointer, is it really make your programs faster? There are also some cases that you probably don't want to use pointer intensive data structures. So from now to the end of the semester quarter, we are going to talk a lot of this example. So sometimes if you cannot answer those intensive C or C++ tricky C or C++ programming language, don't be too sad. It's just because you are potentially a better programmer. All right. So also, right, one of the questions that I got asked is that, okay, so this also shows up in your midterm, right? Like, why adding a sort would make the whole program faster, right? And for that particular multiple choice question, you guys know that, well, with a sort, the instruction count is more. So it sounds like, okay, its execution time is slower. However, because the CPI is also lower on average after you added a sort. So turns out the performance is better, right? So, okay, we know this, but we don't know why. So now, this following series of lectures, we are going to tell you why. So the high-level topic today we are going to talk about is the pipeline processor and pipeline hazards. But before we talk about pipeline processor, you cannot skip the very basic processor design idea. And some of you who might heard a lot of story from students who took 141 before, or even your CSE30 might give you a nightmare on this kind of stuff. And for today, we are not going to talk about too much detail about that. We're only going to give you a very high-level idea, because it's more important that we capture the high-level idea of the processor design. But I intentionally skipped the volume architecture slides for a reason, because it's showing up now. Okay, so we talk about if we want to talk about basic processor design, right? You cannot forget how your computer executes your program. So first, again, right? You remember everything must be presented in the memory, right? And then your processor, what your processor would do? Your processor, once you got everything in the memory, what's the next thing to do? What's the next thing to do? Fetch instruction, and then fetch data. What else? Store it. What else? Okay, so there are quite a few things you want to do, right? So in fact, right, you need to perform this logic operations. You need to perform this arithmetic operation. You need to perform memory operations, right? And also you have branch instructions that help you to change the control flow of your program, right? And it's abstracted by instruction set architecture. So the whole thing, one of the big part of the processor is that we have logics that implements support for the instruction set architecture that this processor should expose to the software, right? So that's the high level idea of a processor, is basically first a collection of functional units. However, if you look at, okay, what do I have to do before and after I get an instruction? Here is the list of things, as many of you said, because everything comes from the memory. So the very first thing that I need to do is that I have to fetch the instruction from the memory. And then, okay, simply fetching the instruction from the memory doesn't solve the problem, because the processor has to know what do you really want the processor to do. And that stage is called decode. So there are two purposes of decode. First is to figure out what kind of operations, no matter it's arithmetic, memory operation, or conditional jump. You have to figure that out to pick the right ALU, right functional unit to execute that instruction. And the second thing, right, you also need to figure out where the data are coming from. Are they from the register values on the processor? And if that's the case, I need to prepare this value for the LU to retrieve it. Or is it from the memory, right? So, and if it's from the memory, how can I find what kind of source that I can use to find the effective address? So those are the stuff that at the decode stage that you need to do. And then the next thing is called execution. And for execution, depending on what kind of instructions you are doing, you are performing, there will be different functional units being used. So for example, if it's just ALU operations, for example, arithmetic operations like summation, addition, subtraction, multiplication, division, this you would directly use the functional units that's corresponding to it, right? Or it's logical operation like exclusive OR you just heard, right? You will use LU for it. However, if it's conditional branch, for example, should I jump? Should I not jump? Should I pick C or should I not pick C, right? So this kind of question, it should be answered by a branch unit. And memory instructions determine if it's a memory instruction, you might think, okay, for memory instructions, shouldn't I just access memory? But you guys remember the x86 format we have, right? You have a base register, you have a multiply, you have an index, right? So you need to put these three things together to calculate your effective address, which also require the arithmetic unit. So they would actually have, modern processor, they typically have another unit to calculate this effective memory address. And finally, for memory operations, once I got this effective memory address, then I can start access the data memory, right? And then if my instruction is generating a result that the instruction intentionally want to leave it for future instruction to use, they will write the result to a register on the processor, and that's called write back. And don't forget, right? When you finish an instruction, you need to move on, right? Move on is very important, right? Move on is very important. So yeah, it took me a lot of time to move on. Okay, that's a long story. But the thing is that move on, right? If you don't move on, you are going to stuck in the same place, right? Not making progress, right? So here's the thing. After you finish an instruction, don't execute the same instruction again. You have to move on. But how do you move on? You have to update a PC, right? It's pretty simple, right? Just go to the next. Or if the branch is taken, change your address to the branch target address, right? So those are two cases when you move on, right? You can either move on the branch target or the next, right? So that's the life of an instruction. So based on this is the functional units, an overview of the processor we have, right? So because you want to fetch an instruction, and how do we know which instruction to fetch? So there must be a program counter giving you the address to the instruction fetch unit. And the instruction fetch unit would ask the memory. And in modern processor, it's typically something called cache, right? So I will consult the cache for the instruction we want. And how the cache get the real stuff that you want is actually the story that you'll learn a lot in the previous 2 weeks, right? And once I fetch this instruction, I will send it to the instruction decode unit. And the instruction decode unit would work together with the register file to figure out what are the inputs that I should put into this functional units. And once I'm done, I would either change the program counter or update my result to a register, right? So that's the high-level idea of a processor. And a lot of you learn CS140, right? So you know, okay, if I have a processor, if it's clock, what will happen is that every clock I would run every clock I would probably run or one of these things or the whole thing, right? And once I finish one instruction, I will go to another instruction, right? So in a very conventional design, the operation of your instructions, they are back-to-back, they are serial, there's no parallelism. So fewer number of instructions, instruction count would actually means better performance, right? That was the past. That was the past. That was the past. That was the past. I want to say that again and again, because that explains why some of the code optimizations doesn't work out anymore, because that was the past. Right now, no one is actually using that kind of processor design. Most of the processors are so-called pipeline processor. So, you know, pipeline, that's why this is related, right? This is pipeline. Okay, if you haven't watched the movie, try to find that movie. It's really an entertaining one. I highly suggest it. Okay, good. I don't know how much money I got from them. Apparently 0. Okay, so here's the thing, right? Pipelining is a hardware mechanism. In the hardware design, actually there are software pipelining, but it's a separate topic that we can talk about in parallel programming. But for hardware pipelining, the idea is that instead of doing all the things one at a time, I break up the subtask within the task into different pieces. And every time I only make small amount of progress. And what's the good thing about that is that once you break up your logic to big logic to small logic that perform a subtask, what you will do is that every cycle, you just work on the subtask. And once you are done with the subtask, you just yield your resource of that subtask to the upcoming request, instead of having the whole processor idling and waiting the completion of the current operation. So this sounds very, very, very vague, right? So let me give you a graphical representation. So this is a clock, right? Clock, as you can tell, this is a clock. Okay, so what will happen is that you break up your logic with a hardware unit called pipeline registers. And what will happen is the clock would connect together with those pipeline registers. So it's a signal. So whenever the clock begins, they would trigger this hardware units to start working. So for example, if I have an instruction like this red instruction, and with this pipeline, it's basically saying that, okay, we are dividing your task into 5 different pieces. So for this one, right? So the cycle 1, I only make 1 out of this 5 progress inside the pipeline for the red request. And now when the second cycle comes in, right? The red one will be moved to the second stage. And the first part of the hardware would be allowed for the orange one to use. And then gradually you advance the red one. And in the meantime, you keep receiving new requests, right? So that's the idea of the pipeline. And because each cycle, you are only doing a smaller amount of things. So your cycle time could be a lot shorter than having the whole instruction finished. So that's why pipelining is in general making your processor more efficient. So if you still feel like pipelining is a very vague idea, I don't know how many of you still eat Subways. And I feel Subways or even Panda Express, they are good examples of pipelining. So if you go to Subways, right, there were typically several attendees. So each attendee is pretty much like a pipeline stage, right? So when you go to the first attendee, what kind of bread, right? I typically would say flat bread, right? Toast it, right? And then done, right? You are going to be moved to the next person, and the next person would ask you what kind of protein, right? Do you want like oven roasted chicken or something, right? Then, okay, done with that. What kind of veggies, right? And then finally the register, right? But remember, when you are done with your oven, well, sorry, choosing your bread, right? You are moved to the next stage, and they can start serving the next one, right? I haven't eaten Panda Express for a long time, so I don't know how they deal with things. But I would bet Panda Express is pretty much this, right? Like, yeah, I don't know. I haven't ordered Panda Express for a long time. All right. Okay, so the idea of pipelining is pretty much like this, right? Whenever a cycle comes, right, your instruction just goes through one stage, right? So it doesn't go all the way down to the end. It just go make a little bit of progress. And then when the next clock cycle come in, right, they move to the next stage, right? And another instruction comes in. And gradually, right, this instruction would advance. But in the meantime, right, look at this animation. Right now, we already have 3 instructions in the pipeline in a processor. And finally, right, the orange comes in, the blue comes in, right? And do we have more? Okay, we do have more, right? And gradually everyone finishes, right? So that's the idea of pipelining. So in the meantime, you can think about like, okay, pipelining is a good idea to keep everyone busy in this processor design. So previously, you remember, right? It takes a lot of time to finish an instruction, but with pipelining, the first instruction may be just doing fetch this, and in the first cycle, but in the second stage, right? The first instruction will become decoding, and the first instruction will be fetching. A second instruction will be fetching, and now at the third cycle, the first instruction will be executing, and the second instruction will be decoding, and the first instruction will be fetching. And gradually, you can see like almost every cycle, we are fetching a new instruction and generating the output of an instruction, right? And so effectively, if you are outputting instruction every cycle, what's the CPI? If 1, right? So, okay, if I design a processor that executes a whole instruction within 1 cycle, what's the CPI? Also 1, right? But with pipelining, your clock cycle is a lot shorter, right? So that's why pipeline processor, it maintains the CPI as a single cycle, very naive processor design. However, your cycle time will be a lot shorter. And because your CT is shorter, so your ET is also shorter, right? That's one thing you learn. So it sounds like pipeline is an ideal idea that if we can keep CPI equal to 1 with a single pipeline, but is it that easy? So why don't you check these pieces of code and tell me how many of them, how many pairs of the instructions are preventing the pipeline from generating results back to back? Question?
Is the theoretical minimum CPI 1?
For that's a good question, but if you have only single set, if you can only fetch one instruction at a time, right? It should be one.
Yeah.
All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after the first poll, okay, I love this figure because it shows that we need discussion. So why don't you guys go ahead, discuss with your friend for another 90 seconds and see how many pairs do you think they are preventing us from getting the pipeline working smoothly. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so after discussion, it looks like this. Okay. Sometimes I made this question because I actually want you guys to get it wrong. But because for example, I feel like people has the most deepest memory regarding something they are suffering, right? So if you get something easily, you'll probably forget it pretty soon, right? But if you suffer from something, right, you probably would remember the most, right? Like, do you remember what's the best food you ever ate? But do you remember what's the worst food you ever ate? You probably do, right? So same thing. Okay. Okay, so for this one, how many pairs, like we have labels, right? 1 through 7. How many pairs do you think they are preventing back-to-back execution? Like, give us some, although some of you pick 1, 2, 3, 4, right? Maybe we unionize things together, you will figure out the answer is probably more, right? So maybe you think it's 2, you think it's 2, but that 2 might be totally different. So what are the ones that you guys have in mind? Which one and which one? Okay. First one and who? The third one. Okay. What situation? First one and the third one. So for the first one, we are outputting to EX, right? And you remember like x86 syntax is really difficult to read. So for this one, we also use EAX as part of the source, right? So you must have this one to finish before you can do this one. But okay, but why is it preventing us from back-to-back execution? Okay, so you think there is a potential they will be problematic in the first run, but why is not an issue for the second run?
It's probably done after
Okay, what else?
the second one
Mm-hmm.
and also the third one.
Okay, right, because this is obviously the case, right? And memory is slow. We all remember, we all agree, right? So this one is moving something from memory to register. And if memory is slow, we have to wait, right? So this may be preventing us from getting, what do we need on time? What else? The fourth and the fifth. The fourth and the fifth. So the fourth is 4 and RDI. And the fifth, okay, again, the fifth is comparing the value of RDI with RDX, right? And without the first, or without the fourth generating the result on time, we cannot make progress. What else? Fifth and a second. Okay, how come? So, oh, sorry, the fifth and the second. Okay, so when you go back, you might use RDI, but that's a good one, right? So you cannot actually, okay, so if you have this run many times, right, you don't want, you have to wait the compare to finish before you can, but are you modifying RDI? No, right? So it doesn't matter. Okay, what else? Fifth and sixth. Okay, so fifth and sixth. How come? Okay, so you need the fifth to set a flag to see if I want to jump or not, right? What else? Which one? Jumping back or moving forward, right? So for 6 and are we going here or are we going here? Okay. So how many is now? 4 or 5, right? There are a lot, right? So let me show you this, right? So sometimes, right? So most of the stuff that you guys capturing are related to something called data dependence, right? Like if I'm generating an output with others, but you know, sometimes there are more than that. So let's look at that. So right now, when I'm executing exclusive OR in this pipeline, right? The first instruction is always good that you can fetch, right? And then after I fetch, I decode, I keep fetching the next one. So to this part, we have no trouble. Now I'm executing the first one and I'm decoding the second one to know what I need, right? To this, I have no trouble and I keep fetching the next instruction. So far, so good, right? Looks like the world is perfect. How come there's a problem, right? So now, once I'm done with my first instruction, I'm going to write back my result to EAX, right? And for the second instruction, okay, I want to do memory operations, right? Because this is a memory instruction, so I'm putting it into the memory pipeline. And for the third instruction, I want to decode it. For the fourth instruction, I want to fetch it, right? So, do you see any problem here? Right. Okay. So that's a good one. So here, right? Okay, look at this. EAX is what we are going to write back. But EAX is also here where we are trying to fetch the value when we decode, right? So Can your hardware support this concurrent operation? Maybe not, right? So this is a problem. What else? What? RDI. Okay, what's wrong with the RDI? You mean this one? But this one is just fetching the instruction, right? I'm not really using the RDI, right? So it's not an issue for now. What else do you have in mind? One thing that is super easy to forget. Where is your instruction coming from? Memory. Where are you going to get your data from? Memory, right? So we have two issues with concurrent access of your register here, also concurrent access of your memory here. So you cannot actually do data memory access and instruction fetch at the same time if you only have one memory unit, right? So that's one problem, right? So both problems are the same now, right? So registers, we have competition. Memory, we have competition, right? So keep going, right? And a lot of you might be noticed that, okay, even though I stopped this one, right? When I want to run instruction 3 into execution, right? I would also figure that out, right? Because for this one, the write back hasn't finished yet, right? So I have no way to get the value of the write ECX for this guy to execute, right? Which you guys already identified when we were discussing initially, right? So that's one of the problems, right? And if you keep going, right, even though we have that address, if we keep going, you will figure out that there are more to go, right? Because like, okay, for here, right, when I'm doing this comparison, right, again, if I want to compare the value of RDI, it's not there yet, right? So because it hasn't been written back, right? And finally, a lot of you think that, well, we can continue fetching instructions. However, whenever you meet a branch, right, conditional branch, like you guys said, because I don't know, we are going back or going forward, right? So you cannot actually fetch the instruction. If you're fetching it, it might be wrong, right? So this is another thing. And do you think that's over? Actually, it's not over. It's never really over, right? Katy Perry, never really over. All right, anyway. All right, so there are many issues here. Like for example, like, okay, instruction 6 may not have the outcome from instruction 5 to make a decision, right? So those are the stuff. So turns out there are 5 pairs of instructions if you count, right? There are 5 pairs of instructions that are preventing you from making the pipeline working smoothly. So although we were thinking about ideally the pipeline can maintain a CPI equal to 1, but without appropriate architectural support or good programming technique, CPI equal to 1 is just a dream. Just like a dream, right? There must be a song like that. I have to find that one out. All right. And so, you know, people like to categorize things, right? Like you have 3 sources of cache misses. We also have 3 sources that prevent pipeline from making progress. That's called 3 type of pipeline hazards. And these 3 type of pipeline hazards, they are these 3: structural hazard, control hazard, and data hazard. So by structural hazard, it means that resource conflicts cannot support simultaneous execution of instructions in a pipeline. So if you only have 2 hands, how can you handle the third stuff, right? So that's structural hazard by human beings. Again, so for your processor, your hardware, if my memory unit can only support 1 request at the same time, how can I support 2 concurrent access, 1 for instruction, the other for data? Or if your register have only 1 set of cells, how can you allowing both read and write at the same cycle, right? So those are so-called structural hazards. They occur just because the hardware has their own limitation. And your code is actually asking more than the hardware can do because of you want to pipeline the instructions. So if you hear this carefully, right? If you don't pipeline stuff, all the above issues that I mentioned won't occur, right? Because if there's only one instruction at any time that is currently running, there is no issue with, there will be no structural hazard because you only have one that can exclusively enjoy all the resources. Same thing, control hazard, right? So one key thing that we want to keep the pipeline moving is that we have the ability to continuously fetching instructions before instructions finishes, right? So as you can see, if you have a 4-stage of pipeline, your fourth instructions are already in the pipeline before the first instruction finishes, right? And if so, and the key thing is that you have the ability to continuously fetching, but there is one type of situation preventing us from making that happen is that if you have conditional branch that can potentially change your direction, right? Then that's causing a control hazard. So for example, if you want to graduate, right? But there is a condition called passing or not, right? It's like a conditional branch, right? That will change your projection about your life, right? So this is control hazard. Finally, data hazard. So data hazard means that an instruction, depending on a result that is not yet generated in the pipeline, if you directly go ahead and it's queued, you are going to get the wrong result, right? So that's called data hazards. When your later instruction is depending on the earlier instruction, however, at this moment, if you go ahead and it's queued without that correct input, you are going to generate the wrong result. That's data hazard, right? So these are 3 types of pipeline hazard. And as you know, this kind of question would definitely be part of the short answer questions. So, okay, question?
Is it common for modern day processors to only have one memory unit?
So that's what we are going to talk about later. But, you know, look at this, right? So can you tell like for, okay. So why do I have this question? Okay. So for this question that the same pieces of code that we have seen, right? Can you tell me how many of them are pipeline hazards? Sorry, data hazards. This is exactly the same pieces of code. And we say there are 5 pairs are problematic, but how many of them here are data hazards? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so, okay. Can we have a quick discussion? So maybe, you know, sometimes the 4 you are thinking may be different from the 4 that other people are thinking. Go. Forget about the timer. I think I didn't set the animation correctly. Oops. Anyway, sometimes too many animation is an issue. All right. Discuss. I want to hear your voice. Louder, louder. Does it help? All right, let's wrap up in 15 seconds. All right, 5 seconds. 3, 2, 1. Time is up. Okay, so let's take a look. Okay, what do you guys have? What do you guys have in mind? Number 2 and number 3, right? And they are both using ECX, and we have to wait for this one, right? So it's completely a data hazard, right? Because if you have this one, go ahead and run in the pipeline, it's not going to work, right? You are going to get an outdated result for ECX. What else? Number 4 and number 5. So for number 4 and number 5, right, you want to compare RDI. And if you don't get the right value of RDI, right? Okay, what else? Number 5 and number 6, right? Because you want to get the outcome from 5 to make the right judgment, right? So this is a hidden one, right? So turns out there are, oh boy. Sometimes I hate too many of my animation in this way. So turns out, right, for this one, we actually should have a few of them, right? So first of all, right, as we mentioned, if we only have 1 unit of memory or 1 unit of register, that turns out would give you a structural hazard, right? And for this case, right, we don't know where to fetch. That's a control hazard, right? However, the remaining, this one, and this one, they should be data hazard, right? As you just mentioned. So we have 3 of them are data hazards. Okay, so now let's move on to the next question, which is actually coherent to the very first question we have in the class today. For this one, what's the main cause of slowdown in version B compared against version A? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Let's see. The answer is B. What is B? Data hazards. right? So again, right? As many of you already know, right? Like, okay, if your code pretty much like the right-hand side, right? After you're done with this one has to read this one and this one, right? So they are back to back, right? And there's nothing can be overlapping. However, for this one, right? Um, although it sounds like there are also dependencies. However, if you look at the gap between dependency, right? So for temp, it's used by two statements later, right? So there is actually some kind of dependency being separated, right? So there's a gap. So it has less potential to result in data hazard if it's a pipeline, right? So that's why the right-hand side has worse performance. So that's why I'm saying prioritize to the era of pipelining. Probably the left-hand side is going to be slower because it requires more register, or sometimes if you're unlucky that you have a machine without that many register, then the left-hand side would probably be indeed slower. However, on the right-hand side, right, you are having, if everything is just one cycle, right, maybe you can have some optimizations that only needs 3 instructions or something, right? So turns out that the performance of right-hand side right now is not better than the left-hand side, right? So if today there's a programmer tell you like the right-hand side is better, then that programmer must be fired because looks like that programmer is generating inefficient programs. Okay, so we hate hazards, we hate issues, and as an engineer, our mission is problem solving, right? We are problem solver. Sometimes we create problems, I agree, right? Like, like being a software programmer, your life is probably write bugs in the morning and debug in the afternoon and write another bug for another day, right? But half of our, at least half of our life is trying to do problem solving. Okay, so if you want to solve this problem of pipeline hazard, there is a universal solution. Okay, again, sometimes a solution doesn't mean it's a good solution, right? So the very first solution that will solve every type of hazard is called stall, right? And that's probably something that people would like to do. Whenever you meet a problem, okay, let's just wait and see, right? So what will happen here is that, okay, so the very first idea is that whenever I see there is a situation that doesn't allow me to proceed, I just wait. Instead of like being aggressive, I just wait and see what's going on, right? So what will happen here is that, okay, you can imagine there is some kind of hardware. If it detects there's a potential of any kind of hazard, I just stop. So for example, right, we were saying that the very first pipeline hazard we have is probably like at this point, right? So we found we cannot write back at this time because EAX is also, we were not sure if we want to write back or instruction decode. So at this point, right, we just let the write back because it's an early one. So we let it proceed. However, the one with structural hazard, we just stall it. By stall, it means that, okay, right now it's entering this stage, but we never make progress of it. So you can consider that you have some kind of hardware logic that disable the update to the register at this time. So then you are staying at the decode stage. And right now here, another instruction is write back, right? So I'm also like keep decoding instead of, because this time I'm writing back ECX, right? So again, right, even though I stall for one, I would have another structural hazard because we are both competing with ECX. So at this time, I just keep stalling until both are addressed. I can finally finish my decode and then I can continue, right? So this is the idea of stall. I just keep waiting for people who are elder in terms of the sequence of execution to solve the problems, and then I enjoy it, right? So that's pretty much the idea of stall, right? You did this a lot in your life, I believe, right? Whenever you break the glasses, right, on the ground, right, you just leave, and your parents would would yell at you, but they will collect it, right? Something like that. Anyway, all right. So this is the idea of stall, right? But if you stall on every place that you meet such a problem, we're going to have significant slowdown on the performance, right? So for example, although we imagine that each instruction would take on average 1 cycle to execute. However, if you look at this, right, if you want to implement stall, you will have to pay 5 additional cycles, which means that you are probably going to spend like 15 more cycles for this sequence of instructions, which would completely diminish the benefits you can get from pipelining, right? So you don't want this. So we have to aggressively solve the problem as a programmer, as an architect, as a system designer. So to solve the structural hazard, right? The main issue with structural hazard is just because your hardware cannot handle it. So if you want to solve structural hazard, the easiest way is that the hardware handle it. So a few examples, right? So for example, the first structural hazard we met is actually the conflicts between instruction decode and write back. Both of them needs to access the register file. However, fortunately, here's the trick in digital design. Register is one of the fastest hardware components in terms of digital design. And it's typically shorter than your cycle time. So a technique that actually a lot of hardware designer is doing is that, okay, I just consider, and if you learned CSE140 before, right, you must remember the cycle is actually a rising edge and fallen edge, right? So what we are doing is that, okay, for the rising edge, we consider it as the first half, and the fallen edge, we consider it as the second half. So on the first half of the cycle, we add an earlier instruction to update the register. And for the second half, we allow the later instruction to proceed with reading. So this design has 2 benefits. First, well, some of you might be asking, why shouldn't we flip the order? And the answer is, if you don't flip the order, right, you let the earlier instruction update later, then potentially, what if the later instruction wants the output from the earlier instruction, right? You have to store anyway. So the truth is that you have to let the early instruction to complete its job first, so that you can directly enjoy the benefit of write back, which a later instruction may be needed, right? So that's why you write first and read later. So that's the first design we have, right? And this is actually by default our design. Now, the second problem we have is, how about concurrent access to memory? And that actually, you already know the answer, is that we just separate the instruction memory and data memory management unit. So it turns out every processor right now has a split instruction cache and data cache. And the reason is actually because there are 2 reasons. First reason is because if you think about the behavior of instruction and data itself, they are very different. So instructions have very strong locality. Like if you have loop, that's strong temporal locality. If you just keep going, that's strong spatial locality. And if you have to mix that with data cache, right, that would actually break the locality or kick out stuff a lot. And you actually want the instruction to supply smoothly. So it's a good idea to split the instruction and data anyway. And the second, which is also a main reason why we want the split design, is that now you can avoid the structural hazard between instruction fetch and data memory access, because they are physically two different front ends to your processor. So that's why you look at the memory hierarchy now, it's always a split L1 cache, and but unified later, because L1 cache, all we want is that we want the instruction supply to be uninterruptible. So that's why the split design is universal now. So with that, right, you can imagine, okay, our microprocessor is revised in this way, right? So you have a split cache. Okay. So now, okay. So far we were imagining that the memory operation would be the same speed as other operations. But in fact, in many cases, right, your instruction might have different lengths, right? And if you allow one of them, if in this case, right, so saying that, okay, now, if my memory instruction needs 2 cycles to finish instead of 1, right, consider like, okay, what do you measure, right? Like L1 cache hit rate is 4 cycles. But right now, I'm assuming simply saying that it's 2 cycles, right? Then what will happen, right? So if you do not respect that part, what will happen is that, right, this instruction, it takes 2 cycles to write back its result, to get to the write back state. And another instruction takes only 1 cycle. So it turns out they will hit each other in the write back stage, right? So you cannot let that happen. So another thing in a single instruction pipeline we typically do is that we have to ensure every instruction needs to have exactly the same amount of pipeline stages. So it turns out what you will have to do is that, okay, even though execution doesn't take so much time, the EX instruction, the LU instruction, they still have to wait for 2 cycles to write back the result to avoid this kind of structural hazard. So that's also one mechanism of avoiding structural hazard. So as you can hear, right, everything we can do about structural hazard are from the hardware part. You can split your L1 cache. You can change your register file design. You can force all instructions to be going through the same amount of pipeline stages, right? So not too much as a CS student we can do, right? So we are not going to talk too much about a structural hazard for now. Question? Okay, but there are other hazards that we can deal with. The first one is called control hazard. So control hazard is the case where we cannot know if we can fetch 7 or 2 before EX is done, right? For example, right? So this is the case of control hazard, right? So, and the reason why we have control hazard is whenever we have a branch. You might think it's branch that often. And in fact, it's very often. Okay, so you must be offended by this amount of code that I'm giving you here. But again, this is the code. It will show up on your lab 3, which I will publish tonight. And but if you compile the code, even though this is like a pretty optimized code, you will see like, okay, there are many places that we need branch instructions. So for example, you want to know if I am smaller than the repeat, right? So you need a branch for that, right? Because if it's greater than that number, I will jump to the end of the code, right? You also want to know if it's smaller than size, right? Then you will have corresponding code regions to make that judgment, and also the target for it. And also, right, if you look at where the branch is jumping to, right, there are 2 types of branches. One is called forward branch. By forward, it means that in the order of your code, if the target is going to a label that is on the forward direction, that's a forward branch. So for example, this one is jumping to L4 and L4 is after. And typically, the forward branch would appear in the case where you are implementing if-else statement. And for backward branch is the case where the target is actually some label that's backward in terms of the location, right? So for this one, if it's jumping back to L6, it's a backward branch. And whenever you see a loop, that's when you will need a backward branch, right? So sometimes you think, oh, there are so many branch instructions. How can I tell which one map to which one? First, look at its direction. If it's backward, it must be related to a loop. If it's a forward, that's typically a if-else statement, right? So, but anyway, your code has a lot of branches. And if you look at these pieces of code, right, you have on average 5 instructions, one branch per 5 instructions. So it's a lot in your code, right? Okay, so well, and its impact is a lot, and there are things that we cannot avoid it. So we are going to dip into more detail about branch in the next lecture. But before you leave the classroom, a few things that I want to talk to you about. So, you know, this is summer session, and I know a lot of you have a lot of things to do, but don't forget, taking course is your duty, and don't have time doing something is never a reason, because time management is very important. Like, and it's actually a skill you have to learn to become a very successful young professional. So, you know, don't be childish. You have to grow up, and you know, you have to suffer to remember the skill of time management, right? So, unfortunately, this is something that you have to learn, and I cannot help you with that because I also have my job. I want to teach you these things, right? So, and the reason why I'm saying this because we have 2 upcoming due days. We have assignment 3 due this Sunday. We have lab 2 due this Thursday. All right. So, if you don't have any other question, I will talk to you tomorrow